Okay, welcome back. So now we're in the 410. We're kind of out of the proof stuff. I'd love to spend more time on proofs because it's such a nightmare for me going through college, not knowing anything about proofs personally. Um, but if you end up having to be a math major or something like that, you probably want to read the rest of that section. If not, then that's cool too. But yeah. So anyways, 4.10, now we'll start talking about some computer stuff. And hopefully you visited, you took my advice and went to that Python thing and Code Academy and tried some of that stuff. I'm hoping, even if you didn't, you'll be all right, just based off what we have in the book. So the book uses like a pseudocode, so it's not really a code. All languages are kind of alike, if you ask me. If then, if then else. So the first thing I ever programmed was in BASIC, and that was back in the day. We had these TRS-80s, and so just used a TV for your monitor, and it would be hooked up to that, and you used if-then statements and go-to statements and stuff like that, and everything was numbered. So every line was numbered, and you would go to line whatever, and you'd write like corny little programs like Russian roulette and stuff like that. They had more complicated programs, but usually I would, if I wanted something like Centipede or something like that, I would have to have that written on a cassette tape, is what we were using for to record the programs. So, I, like the next language I learned was probably a while after that. That was that Java. And then once I left college, I got more interested in like Turing machines, so I would be able to do theoretical computing and try to figure out what a computer could figure out and what a computer couldn't figure out. And yeah, I mean, I did all that on my own. I didn't take any classes for that, but did a lot of that stuff. And all of the programs, in my opinion, are the same. Python is pretty much the same as Java. They all have the same flavor. So if you just do the pseudocode, you'll be all right. We don't need it to run or anything. We're going to explain it too. So if you're an experienced programmer, hopefully I'm not insulting you with the level of simplicity here. I've had some programmers in my class before, and they said I was doing an okay job. So let me know. All right, so the first example, 410.1, is an example of an if statement and with an else also applied to it. So you imagine a user is typing in a number and the computer is retrieving that number and then it sends it through this code. Okay, so the computer asks itself, is the number that you gave me X greater than 2? So when it is, then you execute this next part. Then you say, then let's call Y X plus 1. Okay, so whatever X is, you just add 1 to it, and that's what your Y will be. If X is not greater than 2, we'll execute this else do code. Okay, so that code is X is X minus 1, and then Y we'll say is 3 times the new X. Okay, so you can imagine, at least in Turing machines, you're writing on a tape. Okay, and as soon as you do this part right here, this X is now X minus 1, you've written over that part of the tape. Okay, so you've replaced the X with this new value X minus 1, and then when you go to this Y part, you're multiplying 3 times the new X. Okay, so it's whatever was put into the slot last is kind of what you're executing. Okay. One thing that helps a lot are kind of visual diagrams of the code, so as a flow chart, in other words. So basically the computer is making decisions based off of some questions, right? So the first question, a user puts in a number and that number goes into here, and the computer asks itself, is that number greater than 2? It's either yes or no, right? So if it's yes, then you're going to do I mean, just literally listen to what I'm saying. If yes, then you do this, right? So if yes, then our y is going to be defined as whatever x was, okay, plus 1. If no, then you do the else do code. Okay, then you do this code right here. So you'll redefine x to be x minus 1, and then you'll define y to be 3 times the new x. That's the result of that previous part, this part here. Okay, so the homework will have you run the code with particular given values from the user. So, for instance, part I in the book, under this guy, the user is typing in 5. Okay, so we want to know what x and y will be when the user types in 5. So when 5 goes in the machine, okay, and we can kind of trace the flow chart here. Sends in 5. Is 5 greater than 2? Well, yeah, certainly. So it's going to go yes. And then y will be equal to 5 plus 1. So y at the end of the code will be equal to 6. All right, x is still 5. Okay. With an actual computer program, you would have to then, maybe print. So in Python, you have to type print and then whatever it is you're printing. Let's do another version here. Let's let x equal 2. So the user types in x equals 2. And for a computer program, you'd have to code the computer to retrieve that user input, and then it will send it into this code. Okay. All right, so let's try green this time. So I'm letting 2 be x, and then the computer asks itself, is 2 greater than 2? And of course that's no. So the code goes over here. It's going to rewrite x now as x minus 1. So at the end, if you ask what x was, it's going to be 2 minus 1, which is 1. Okay. And then you're going to let y equal 3 times x. And so y will equal 3 times the new x value, 1, which will be 3. Okay. And then the output, if you printed to the console, would be 1, x is 1, y is 3. So this x equals 2 gets written over by the new x. Okay, so that's one example. Let's look at part B. Okay, so part B, this time there's no else part of the code. There's just an if code. So basically you don't do anything if the if condition isn't satisfied. So the if code this time, if x is greater than 2, x is greater than 2, sorry, then what do? Well, you're going to assign y to 2 to the x. Okay, so as a flow chart, we could say that, you get a user input, and the computer retrieves that and asks itself, is that value that's being input greater than 2? Okay. Again, there's either a yes or a no, right? So yes, then it'll execute the code. So then it's going to define y as 2 to the x. Otherwise, in this case, it doesn't do anything. It'll just hopefully just end the program. Okay, so again, the book gives us some values for x. That would be user input values, or maybe some input from another part of the program. Let's say x is 5. Okay, so I'm plugging 5 into here. Is 5 greater than 2? Well, yes. Okay, so 5 goes into here, and then it'll define y to be 2 to the 5th. Okay, so at the end of the day, y will be 2 to the 5th. If you wish, 32, right? Secondly, then, the book wants you to try x is 2. Okay, so we'll take 2, and that will go into the machine, and the machine says, is 2 greater than 2? Of course, that's not true. Okay, so you'll be going down this direction, and you just stop the program. Okay, so in that case, y is still 0. Okay, so initially the y value was set to be 0. It's defined in the first part of the program. Okay, so here we did not write over y like we did with the yellow computation. We wrote over y and replaced it with 2 to the 5th. So originally it was 0, but then it ended up at 2 to the 5th. Okay. All right, so hopefully that's somewhat understandable. Let's now work with more complicated statements. So if you take a data structure class, I guess you'll do like sorting, and I don't. It seems like maybe we do a little bit, but not really. This chapter, we'll just set up an algorithm for finding greatest common divisors. Okay. But anyways, iterated statements. These are ones that will kind of repeat over and over until you hit some sort of condition. Okay, so iterated statements. And all a computer algorithm is, at least to me, is just a set of instructions. Okay, so at the beginning of the century, it was like Turing was trying to figure out whether or not you could decide certain things with a computer. And so it was just a set of instructions, and you could kind of code it into math symbols and analyze it. And I don't know. So an algorithm is literally just a set of instructions, and that way it's kind of like human thought. You know, if you could literally think of everything you do as a set of instructions, that stuff is codable. You know, you can get a computer to do it. And the question is, can you get a computer to do pretty much anything a human can do? And that goes along with my AI stuff. So again, the AI folder, if you want to read one of those articles and do like a 2-page paper, I'll give you like 10 points. Just a maximum of 10 points. You can't do like 5 papers and get 50 points. And some of those papers are pretty long and technical, so if they're too hard for you, just let me know and I'll send you an easier paper. But you can always probably just do the Python and Code Academy, at least if you get up to like the pig Latin stuff, or maybe the grocery list problem in there. I'll probably give you like 10 points for that, but max 10 points for extra credit. Anyways, iterated statements, the while loop. So in this case, you'll keep repeating while some value is below some other value. Okay, so in particular, example 4.10.2. Okay, let's look at the code there. They initialize the variable I to be 1, and then the variable s to be 0. And then they say while something is true, you'll execute the following code. So in this case, while I is less than or equal to 2, you're going to do the following. You're going to say redefine or write over s and make that s plus I, and then write over I and make that I plus 1. Okay. Once I exceeds 2, then you'll end the loop. Okay, so you'll say end while. Again, we can do kind of a nice flow chart for this. Okay. So you're continually asking yourself, is I less than or equal to 2? And of course, there'll be a yes or a no. So if yes, then you end the program. Sorry, if yes, then you're not done. If it's still less than or equal to 2, then you're going to be executing this right over I is I plus 1. And then you're going to go back to this condition and keep asking that and keep looping around until I is no longer less than or equal to 2. And then that'll be the end, right? Okay, so you could do a flow chart. In the homework and web assign, they're going to ask you to do trace tables. Okay, so doing a trace table, is good for these kind of loopy structures. And I think within even computer programming, I don't know if people really do trace tables or if there's some standard way of doing them. But basically you'll be counting the iteration or the loop value. Sometimes they'll call that n. And then you want to label the other variables that are in your program. So we have an I and an S, right? And we'll start with 0 before it kind of goes into the loop. And the I and the S were initialized to what values? 1 and 0. Okay, so it goes into the while loop with 1 and 0 for I and S. And we ask ourselves, is 1 less than or equal to 2? That's true. So S will now be S plus I. So S plus I is going to be 1. Okay, so this is in our first iteration. And then I gets redefined as 2. Okay, and then it comes back out and goes to the condition. Okay, so it's going to come back out here and go back and ask, is I less than or equal to 2 again? So I is 2. That is definitely less than or equal to 2. So it goes back into the loop for the second iteration. And again, S will be S plus I, which will now be 3. And then we add 1 to I. So that'll be 3. Okay, and then it comes back out again, back to the initial condition, and it says, is 2 less than or equal to 2? Or sorry, I is 3 now, so is I less than or equal to 3? And that's of course no. So we end up going down here to end. Okay, so at the end, our outputs for I is equal to 3 and S is equal to 3 as well. Another one that's kind of similar to the while loop, instead of having a condition here, it just kind of tells you go from this number to this number, and it'll tell you how to increment. Different coding languages obviously accomplish these things differently, but this is kind of our pseudocode, so we're just going to go with this. So for next, example 4.10.3. So we have for I going from 1 to 4, and in Python you don't even necessarily, so it's for like you can let this thing be a list of numbers or something like that, and it'll go for some key in some dictionary. We're traveling through these, and that's pretty much all you have to write. But for this code, you kind of have to increment it, right? So for I equal 1 to 4, you're going to execute the code x is I squared. Okay, and then you'll increment I. So you'll add 1 to I and then loop back around until I gets through 4. So let's try this one again. And the flow, we could do a flow diagram if that helps. So the first part is asking basically, is I less than or equal to 4? So this code here will run from I equals 1, 2, 3, 4. When I is 4, it'll still execute. Okay, so it's not like a inclusive thing. It's including the endpoint. All right. So if this is true, then you're going to execute this right over. So replace x with I squared, and then it'll send back. It'll go back to the original condition. Okay, but in the process, it'll add 1 to I. So it'll go I plus 1. Maybe I should kind of spackle that on right here. So I is now I plus 1, and that's what next I means. Okay, if yes, if no, then you're kind of done with the program, right? So end. Okay, so let's do a trace table for this case, and I is going to be initialized to 1. So here this part will define I to be 1 in the beginning. So we have our iteration, we have I, and then we have X. Okay. Okay, so iteration 0, I is at 1, and X is not even defined. Okay. Iteration 1, now we're going into the code, and X will be I squared. So we have 1 squared is 1, and then we add 1 to I, that'll be 2. Okay. Iteration 2, so now we let X be 4, and then we iterate I to 3, and we're always checking, is I less than or equal to 4 before the next iteration, and I this time is 3, so it still works. So X will be 9, and then I will go to 4. I is still less than or equal to 4, so I execute again. That'll make X 16, and then I will be 5. And finally, I is bigger than 4, so it'll jump out. And in the end, our I is sitting at 5, and the X value is 16. Okay. Okay. Another big thing, if back to my my quote-unquote research with computer integration systems, and the division algorithm plays a pretty hefty role in that, because what a lot of the integration of techniques, what the integration technique they use in computer programs is it's mainly a partial fraction decomposition, and to get there they do long division. Okay, so if the numerator is exceeding the denominator, you do long division, and that will be this division algorithm, sort of. And the quotient remainder theorem is kind of what I would say. But if you're not taking calculus, then this is all lost on you, so I'll just get on with it. And you could think of this more as a number theoretical type thing. So we're going after the division algorithm, and we're going to start with the quotient remainder theorem. And I believe the quotient remainder theorem is kind of attached to the unique factorization idea. So if you're not in a unique factorization domain, you're kind of out of luck. You can't use the quotient remainder theorem, which is bad if you're trying to do this sort of division for figuring out an integral. Okay, if you're taking calculus, you know what that means. If not, that's okay. Okay, so the quotient remainder theorem is saying for all n, and this is in the book, it's just one of the sections we skipped, for all integers n and d and the positive integers, there exists a unique q and r in the integers such that you can break n down into d times q plus this remainder r, and also 0 is less than or equal to r is less than d, so just strictly less than d. Okay, we can use that then this division algorithm to get later to the Euclidean algorithm, which will find us the greatest common denominators. So first things first, the division algorithm. Okay. So this is algorithm, let me scroll up a bit before we, okay, so algorithm 4.10.1, division algorithm, and it'll give you these numbers in this in the prior expression that we want, in particular the q and the r, the unique q's and r's that will result if you tried to rewrite n in this way. Okay, so if we want to know the q and r, you can use the division algorithm to figure that out. Okay, so what is the algorithm? It starts with all these are written kind of the same way in the book. There's an input from the user, so you'll have this a value in the positive integers and a d value in the positive integers, and then the body of the algorithm. So the set of instructions that you follow, they'll define r to be a, and then set q equal to 0, and then they have a while statement. So while r is greater than or equal to d, r will be defined to be, maybe I should indent on that thing. Sorry, stupid pen isn't working on me. It works all the time when I don't want it to work, but now that I want it to work. Okay, well, that's as good as it's going to get. Okay, so I'm going to, while r is greater than or equal to d, we're going to let r be redefined as r minus d, and then q be redefined as q plus 1. And then once it's not true, you'll end the loop. And then the output will be q and r, and those will be in the positive integers. Okay, so that will give you the unique values such that your whatever, I guess a will equal d times q plus r. Okay, so a in this case is that n value. All right, so let's try this. The book is going to want a trace. Okay, so this is example 4.10.4. In particular, they want to see what happens with a equals 19 and then d equals 4. Okay, so our variables, I'll put n for the iteration, and then we have an a, we have a d, we have an r, and we have a q in order of, I believe, appearance. Yeah, so just put them in order of appearance in the code. Okay. Okay, so start with iteration 0. A is given as 19. D is given as 4. So R will be A 19, and then Q will be set to 0. Okay, so iteration 1 is R. So we have to ask ourselves, over here, is R greater than or equal to D? And so long as that's true, we'll keep on doing the code. Okay, so for iteration 1 is 19 greater than or equal to 4. And yeah, that's true. So you rewrite R as 19 minus 4, which is 15. You rewrite Q as Q plus 1, so that would be 1. Everything else is the same, so you just carry it over. Okay, is R still greater than D? Yes, that's true. So 15 minus 4 is 11. And Q now is 2. And everything else is the same. Is R greater than D? So 11 is greater than 4. Yes, so you take 11 and subtract 4 and put it here. 7, 8, 9, 10, 11. And Q will increment by 1, and then 4 and 19 are still the same. Okay, is 7 greater than or equal to 4? Yeah, that's true. So R will be 7 minus 4, which is 3. And Q will be 4. And then this is 4, and this is 19. And then it's not going to work anymore, right? So R now is greater than or equal to D, so we're done. Finally, then our outputs, Q is going to be 4, and r will be 3. In other words, we can rewrite 19 as what was it, q times d, so 4 times 4 plus 3. Okay, so where to from there? Well, we could do that with pretty much what we want to do is find the what are we looking for? The greatest, is it the greatest common divisor? Yeah, we're looking for the greatest common divisor, and there's this thing called the Euclidean algorithm, which is going to allow us to do that. And in order to do the Euclidean algorithm, it's kind of like repetitively doing the division algorithm over and over and over. Okay, so what? Well, let's take a look. Okay, there's a couple like requirements we have to know how to do as well, but just connecting to the division algorithm, let's say I want to know the greatest common divisor, which we'll call the GCD of I don't know, 21 and 14, right? So we know that to be 7, and the way it's going to work is you use the division algorithm to figure out, 21 is 14 times 1 plus what? So 6, 7, right? And then this 14 will shift over to here. 14 is equal to 7 times 2 plus 0. Okay, and as soon as you get a 0 in this position right here, you're pretty much done. Okay, and then your GCF is going to be this number right here. Okay, in the nutshell, that's the division, the Euclidean algorithm. Okay, this is a real easy example. You could go on and on and on. It will terminate. It's always going to terminate, but that's the idea. Okay, we're not going to be doing the division algorithm in order to figure out Q and R. We're going to use this other function called the modular function, which in computer programming would be that percentage sign, okay, in Python. But here it's going to look like 5. So if you had 5, this percentage sign 3, you'd read it 5 mod 3, and 5 mod 3 is going to be 2. Okay, so how do I figure that out? Well, it's just the remainder when you take 5 and divide it by 3. Okay, so 5 into 3 goes 1 time, and then 5 minus 3 is 2. Okay, so that's the remainder. So let's look at some modular arithmetic problems. Let's try 29 mod 5. Okay. So if you take 29 and divide it by 5, how many times? That's 5 times, right? So that goes into 25. 29 minus 25 is 4, and that's literally our answer. Usually I think of it more like what number will make 29 divisible by 5. So you can think of it as 29, and the way they kind of write this is 29 minus what number is divisible by 5. And we want a number here to be less than 5, okay, from 0 to 5. 0 to 4, sorry. So 29 minus which one of these numbers gives you something that's divisible by 5? Well, 4, right? So 29 minus 4 is 25. 25 is divisible by 4. So 29 mod 5 is 4. It's kind of another way to think about it. Let's look at another one. 16 mod 3. So another way to think of it is the biggest number, such that when you multiply it by 3, is still less than 16. Okay, so that would be, what would that be? Seems like it's 5. But that won't work. It has to be 1. All right, 16 minus 1 is 15. That's divisible by 5. Let's look at the division, right? So 16 divided by 3. Goes into it 5 times. 15, yeah, 1. Okay. So yeah, 16 minus 1 is divisible by 3. There's also another thing, it's called div. So 16 div 3, that's just going to be how many times does 3 go in the 16. So that's actually then this number here is the div. So the remainder is the mod, and this number up top is the div. Okay. So let's just look at a couple more examples of that. Let's say 17 mod 8. That's clearly just 1. Right? 17 minus 1 is 16. That's divisible by 2. I don't know. 21 mod 5. No, let's not do that. Mod 4. Well, that's just 1 as well, right? How about 20 mod 4? So 16, so that's 4. Okay, let's do some divs. 17 div 8 is going to be 2. 33 div 8, so that'll be 4. 32 is the biggest one that goes into. 33 div 7 is also 4. 33 div 6 is then 5. Okay. What is 33 mod 6? Well, 3, right? Okay. Hopefully that'll be good enough. You can just Google search the topic and I'll probably give it to you. Let's go on to the Euclidean algorithm now. And all this stuff is really just clock arithmetic, right? This modular stuff is clock arithmetic. For example, I don't know, it's mod 13, right? So in military time, what is 1400 hours? So you just go 14 mod so I got to figure out what it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's mod 11 is a way of getting from your military time back into civilian time. So what is 14 o'clock? Well, it's 3 o'clock, right? And you can literally count around the clock to figure that out. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Whoops, it's 14. It's crap. Maybe it's mod 12. It's 2 o'clock. That makes more sense. I apologize if I screw that up. I don't feel like making reversing. Let's try another one. So what's 2200 hours in military time? That should be 10. So it would be 10, right? 10 o'clock. Let's see if that's right. So I'm going to count around the clock. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Yeah. There's a cool problem called the Josephus Problem, which is related to all this. So you have like a circle of people, and what you're doing is going around by killing off every other person and trying to predict who will be left. So the idea is you're in some sort of camp, and the guard has rounded up 6 of you, and he's going to go around and kill every other person. You want to figure out where you have to stand so you don't get killed, right? So if he goes by 2s, 1 is okay, 2 is dead, 3 is okay, 4 is dead, 5 is okay, 6 is dead, skip 1, 3 is dead, skip 5, 1 is dead. Okay, so you want to be in position 5. Let's do a different one. 1, 2, 3, 4, 5, 6, 7. Let's get my red pen. Whoops. So 2, 4, 6. You definitely don't want to be an even number, right? And then 1, 1, 2, 1, 2. So you want to be in position 7. And you have to predict, what position, even if you have a number like 80 people, where do I need to stand so I'm the last one standing? It's called the Josephus Problem. And it seems to me it's kind of a modular arithmetic thing. Anyway, so let's do one more mod arithmetic. How about 27? Whoops. 27 mod 5. Right? That's just 2. Right? Okay, so hopefully that's you can, if you don't get it, look in the book, look online. You can always ask me for more examples. Let's just get to the Euclidean algorithm now, which is going to output the greatest common divisor. I'll talk a little bit about the least common multiple in in WebAssign, but we're not going to spend time with that. You sort of figure it out from the directions. So anyways, algorithm 4.10.2, the Euclidean algorithm. So this time you're going to be inputting some a and b, and you're going to automatically define little b to be big B and little a to be big A. The body of the algorithm, then you have a equals big A defined as big A. I guess what I just said. Well, I didn't mean to put this here. I mean to put this in the next line. Sorry. So there are restrictions on A and B, though. A is an integer. A and B are integers. And there's a ordering imposed. A has to be greater than B, which is greater than or equal to 0. Okay, so the body of the algorithm, little a is defined as big A, little b is defined as big B, little r is defined to be big B, and then the actual algorithm. So we have a while statement here. So while b is not equal to 0, let r be equal to a mod b. Let a be equal to b. Let b be equal to r. And then we'll end our while when b is equal to 0. And then the output, it will be the GCD. We need to say let GCD be a, and then our output will be that. Okay, so we want to try this algorithm with the example, or maybe a number in the book. I think it's number 17. I'd have to check that, though. So 1001 and 871. They want us to do a trace diagram with these guys. Okay, so set up your variables. I use n for the iteration, and then in order of appearance, we have an a, we have a b, we have an r, and at the end we'll need a GCD. Okay. All right, so n, hope I got enough room, a, b, r, and then it's like this. So at 0, a is, which one is bigger, b or a? So we want a to be 1001, and b is 871, and then r is set to b, and GCD is not defined. Okay. So while b is b0, b is not 0, so we'll set r to be a mod b. Okay. So maybe we need, there's a bigger number. You can't just do this on your head. 1001 mod b. So how am I going to figure that out? Well, what I do is take, so b is 871. So after going through all that stuff on mod, I still need to explain how to do this. Sad for me. So what do? I take 1001 in my calculator and then divide it by 871. Okay, and then I'm going to take the floor of that. So taking the floor of it just means to get rid of the decimals. So for example, the floor of 5.7 is equal to 5. The floor of 2.01 is equal to 2. So it's like automatic round down. Okay, so you figure this number out, then you're going to multiply it by 871. Okay, times 871, and then subtract 1001. Subtract it from 1001, and that will give you your answer. Okay, so let me get my calculator. Right, so 1001, clear it. 1001 divided by 871 is 1.14 something. Okay, so this will be 1001 minus the floor of 1.14 something times 871, which equals 1001 minus, well, the floor of 1.14 is just going to be 1, and then times 871, and then subtract those, and you get 130. Okay. Your calculator may have a modular button on it, so you don't really have to worry about it. But anyways, getting back to up here, and the formula in general, so I don't have to go ahead and rewrite it all the time. If you have A mod B, to figure it out, you're going to go A minus the floor of A divided by B, times B, right? And that'll give you your answer. Let me get rid of that hook on the top of this. Great. Stupid pen. Okay, so that's our formula for A mod B. Okay, so what? R is equal to A mod B, so R will be redefined as 130. This is the first iteration. Then A is now B, so this you just take this guy and shift him up here, and then B is R. Okay, so R is now 130. It's not 871, so you just put 130 here. Okay, B is not 0 yet, so I do this again, and this time it's 871 mod 130. So 871 divided by 130 is 6.7, so I take 871 minus 130 times 6, and that's equal to 91. So A mod B in that case is 91. I put that for R. And then you do this shift, so 130 goes here, and 91 goes here. Okay, so after a while you don't really need the algorithm anymore. You kind of see the pattern, and okay, 130 mod 91, so 130 divided by 91 is 1.4. The floor of 1.4 is 1, so I'm going 130 minus 91 times 1, which is 39. Okay, so this will be 39. 39 goes here, 91. Still, B is not 0. So you go 91 mod 39. So you take 91 divided by 39. It's 2.3. So the floor of that is 2. So go 91 minus 2 times 39. That'd be 13. Here. B is still not 0. 39 mod 13, that'll be 0 because 39 is divisible by 13. So 0, 0, and then finally 13. Once b is not 0, you jump out of the while loop, so end while, and then the GCD will be recorded as a, which is 13. Okay. All right, that's pretty much how it goes then, and then the program will output the GCD as 13. Good stuff. We'll see you next time.